Good morning again and welcome to Mirabilis Design's webinar on practical applications of system simulation. I'm your host Deepak Shankar and I'm the founder and CEO of Mirabilis Design, and I have about 20 years plus experience in the field of system simulation, especially around hardware, software and networking. Before I get started, I want to go through a few logistics. The first and foremost is there's a section called the chat window on the right hand side in your control panel. Feel free to enter in your questions at any time, and there are people standing by to answer the questions. I'll try to cover those questions as I receive them, but in case I don't, there are people that will hand type the questions and they'll answer it. With this, I'd like to get started. Today what we're going to do is talk about what is system level simulation, the application of system level simulation in computing, storage and communication, looking at different types of modeling methodologies and technologies, how do we interpret the results, and a series of demonstrations that show you how system simulation has been applied in a variety of application areas. A quick introduction to Mirabilis Design. We're a Silicon Valley based software company providing modeling and simulation solutions. We've been around since 2003 and we have support centers outside of the US in China, Japan, Czech Republic and India. Mirabilis Design's products are used to create and design everything digital. So we cover a wide span of market segments, anything from aerospace, automotive, to computing, industrial, and semiconductors. The product is called VisualSim Architect, and we have over 50 customers worldwide. The whole goal of Mirabilis Design is to ensure that you as a user can have the right configuration for your product specification. A quick introduction to why system level simulation is so important and valuable. Let's take a simple design with two processor cores, a DSP and I/O that are connected by two bridges and two buses and a bridge between them. If you take a simple application that has 4 tasks, and you can see the mapping of the tasks going from the I/O via the bus to CPU1, through the bridge to DSP, and then once we're done, back on the bridge to the I/O, and it completes. Now when you look at a complex task sequence of this kind, you can see that there is an input stream, which is some sort of a data or workload, and then there is the mapping of each of these tasks onto one of the hardware platforms, and then there's the scheduling, which is the sequencing of these tasks to these resources. Now, when you have only a single application, it's fairly easy to compute, say, the response time, the utilization of the resources, the effective throughput on the bus, questions such as those. Now, when you start incorporating more number of applications, like right now we have 2 applications. The second one is sequenced with I/O, CPU2, DSP, and then I/O again. So now you can start seeing this considerable amount of contention at the DSP and also at the buses. This is where the scheduling and the arbitration becomes very critical to ensure you don't have certain tasks being blocked by other tasks that may have different levels or higher levels of priority. Now, taking that same design, what we did was we did an experiment where we ran it at 2 different bus speeds, one at 200 megahertz and the other at 400 megahertz. What we found is the latency, which is the time to complete the sequence of tasks, for the 400 megahertz actually had some points in the design where it was actually slower than the 200 megahertz. This unpredictable system response is what system simulation is able to identify and be able to narrowly pinpoint exactly where the problem was. Because one of the things is when you see a problem such as these, where the latency is very high for 400 megahertz versus 200 megahertz, The problem may not lie exactly at that point, but may happen maybe a few periods earlier or maybe even a few tasks earlier. So it's important to understand what was happening in the sequence of events before we got to this high latency. System simulation allows you to be able to run a large number of these variations and try different experiments. A quick introduction to VisualSim. VisualSim is a graphical modeling and simulation software. So I'm just going to open up VisualSim Architect. As you can see, it's a graphical desktop software. There's a sequence of libraries. I can do this. I can do File Open. I can click on this. I can set up a simulator. I can create say drag and drop in a processor. I can attach let's say an axi bus. I can connect a memory device to the same system. I can double click on some of these blocks and modify parameters. You can see this one here is specific to the axi bus. I can go in and make any changes to it. Similarly, if I click on the processor, I can get something that is specific to the attributes that you would have to define a processor as well. So using this, I can create up a much larger system. So here what we're seeing is something where we have 3 audio inputs and 3 audio outputs. And you have a sequence of IAR, FIR, IFFT, things like that. And there's also a feedback loop. Now here what we have is a hardware platform that's made up of 2 cores and a series of accelerators and a memory. Now when we run a model of this kind, we can generate a variety of outputs. Some of them are related to latency, some of them are related to utilization, some of them are related to power consumption, others are timing diagrams. So you can get a variety of plots to be able to analyze how your system is actually performing. You can also get things related to, say, buffer occupancy at a particular hardware accelerator, for example. So what this allows you to do is allows you to determine if a particular configuration is exactly what you're looking for, or is that really what addresses your particular needs. So for example, when I look over here, I can see, for example, this one here, it tells me, the blue lines tells me what's my instantaneous power, which is what is the power at every clock cycle, while the red line shows me what's my average power over the period of the simulation. Now over here on the response time, this tells me how much time it took to go from the sensor to the attenuator, while this one here shows me the amount of MIPS that each one of these what are called block algorithms were taking. So if you take these green ones, which is block algorithm T, you can see that they peak up at almost 350 MIPS. So fairly efficient for a system for a chip that's only about 450, 500 megahertz. You can see also what the utilization is. Now what I can do is I can make changes either through parameters or through text files, and then rerun the simulation to see how the performance is for some other type of configuration. Now, how do we construct these models? We use our large library of stochastic and cycle-accurate components and connect them up together, change parameters, and we run simulations. Why do we run the simulations? Primarily to look at the architecture, where we want to look at the performance, power, and functionality. Now, let's split up our system and take a look at it piece by piece. The first area of interest would be the computing platform. The computing platform is the one where you have your processors, buses, interfaces, accelerators, things like that. The ones we were just looking at right over here, which is this block over here. So and here's where you have your hardware platform where all the compute activity is going on. So it can be accelerators, processors, things like that. That is where you want to look at the key attributes are how do I reduce the power consumption for every task I'm performing? How do I make it more reliable? Do I need a redundant architecture? Do I need to offload some of the tasks onto an additional core? Answering questions like that. From a software perspective, you're looking at do you just want to use the standard VxWorks RTOS that comes up with a first come first serve, or do you want to use like a time space partitioning type architecture and see how the difference or the more increased reliability of your application is on the target system. Now, with the software itself, there's a variety of things. One is that, for the firmware, when the mechanical device is ready, the software should have the data that it can immediately feed to it. So there shouldn't be any delays or bottlenecks when the request comes along. Also, the software has to respond very quickly and accurately to various sensor inputs as well. The second part of the system is we're looking at the storage, and there's a variety of storage systems. So it can be our more traditional storage like disk drives, flash, things like that, or they can be more advanced like a solid state device or a HBM type memory, where we want to look at what is the relative advantage of going with one architecture versus another one. The storage forms a key portion of your timing and your power consumption. So, you activate for your DDR memory, the read and write throughput for sequential versus random latencies. All of those contribute extensively to the overall response time of your particular system. The other piece of storage is really understanding what your interface is going to be. Are we doing PCI Express or NVM? NVM over PCI Express, or are we using a SATA interface? Which ones or which one is more applicable for a target application? Now, when I look at something like this, you can look at the thing where, for example, I can compare a disk drive versus a flash, and I can see, for the same workload and for the same hardware platform, how does it change the performance if I go with one way or the other, both in terms of timing and in terms of power consumption. The other part of it is the network, which you can call it either as the infrastructure, communication, interfaces, any of those. So it can be where I've got a distributed system that is surrounded by or connected together through an Ethernet network, or it can be an IoT application where the Bluetooth device connects them to the hub, or it can be more traditional wireless communication where the bit error rate on your channel has a significant performance impact on your system. So, for example, when I look at, say, just going to go and open up another window, one of the other ones. So this one, for example, is where I'm studying the Bluetooth interface itself, which is the controller, and there is my my Bluetooth finite state machine, and you can see that everything from it starts off from a sleep mode, goes to a wake up preprocessing, and it becomes steady at a low power mode, and then at that point it can receive advertising requests from an external device for it to accept data or to transmit data. So both the transmit and receive can be supported, and Models can be created this way using a finite state machine to describe your control or even your software application. Now, there is the other piece of it, which is the other piece of it, which is, for example, you have two processing modules that are interconnect to Ethernet, but then all the other IOs are and supervisors are connected together through an Ethernet network, which is described here using source destination, what's the distance between them, and what's the speed. So, for example, you can compare twisted pair versus fiber optic. What's the relative difference in both in terms of reliability, in terms of bit error rate, and also in terms of the response time it takes to complete a particular operation or to transfer data. So allows you to be able to evaluate the entire system to look at what my overall response time is, or my overall effective throughput that I can get out of my design. As always, just as a reminder, we have the chat window. Feel free to ask any questions while the presentation is going on. One of the key aspects of the system simulation, especially at the network level, is the IoT devices. So today, IoT devices collect data, just transmit it off directly to a data center. Now, a newer generation of these IoT devices are getting a little more intelligent, where they combine the data, compress the data, or even do some initial pre-processing of the data before it sends it over to the data center. So that way the data center servers are not overloaded, and also you can reduce the bandwidth on the network itself. This here shows you just a coverage of all the libraries available in VisualSim for you to construct models. Now, one of the key things in system simulation to try to understand is what is right for you, meaning what is the type of modeling effort that you want to utilize to be able to answer your questions. Because there's a couple of different ways to look at it. One of them is what's called the level of detail or abstraction that you want to put in the model. So it can be a stochastic model with a workload that is modeling simply the activity around the system without going into the cycle accurate details. So for example, over here, when I look at this particular design, what you're going to see here is a simple mapping with a processor, Axibus, and a DRAM that describes essentially a hardware platform at a cycle accurate level of detail. Now over here, I simply have a network node that is connected to with traffic generators emulating the sensor behavior without putting in the details of, like, say, an analog front end or a microprocessor inside the sensors, things like that. So rather, it's more treated as a delay. So this is the more performance level of abstraction. Then, of course, you have the other one, which is the power. And again, the power can be at a level of detail of where we simply look at the power consumption by just looking at say, a certain set of devices and what's the active and standby power. And then when you run the simulation, so say this Bluetooth device, you can see when I have proximity transfer and a beamer transfer, and what's the instantaneous, which shows me what say, for example, my peak currents look like, and why do I have these kind of peaks over here. And then you can see the average power. Or you can look at something a lot more detail, where I actually have a model of the battery, which is described in a text file. You can select any type of battery, and then of course you can set up different types of charging sequences and things like that with an external charger here. In this case, we are using a constant time-based charger. And so when you run a simulation of this kind, Not only do you see what the instantaneous power is, but also you can see how the how the peak energy is reduced over time, meaning that if I have like a surge current, or my battery life is extended, or the number of duty cycles, things like that will determine what's the life or remaining percentage or remaining amount of joules available in the particular battery. You can also look at what's the remaining battery charge available in the particular system as well. Another aspect of the function of the modeling is the functional correctness. We were looking at the finite state machine. We want to check to see if that flow diagram is correct to handle your Bluetooth mechanism. Another aspect of your system analysis is hardware-software partitioning. Hardware-software partitioning is the process by which you determine whether tasks need to be sent to the processor all the time, or whether I can just create specific accelerators for different subcomponents or sub-functionalities. So for example, over here, this particular thing, I could either have it using this mapping table. I can either send these FFTs over here to the hardware accelerator, or just send them to the processor core and see what the relative performance differences are. Now, when you look at the traditional hardware architecture exploration, you have first and foremost the sizing. The second one is selection of technology. The third one is fully custom designs, where you're designing your arbitration stack, or you're designing a mesh, a topology for the connectivity of all your devices on an SoC, things like that. Again, the other area is looking at thinking ahead. So you're starting to look at what are the potential architectures for the future that would keep a performance going, increasing during every change in the architecture as well. Software behaviors. Typical software architectures are modeled in SysML or UML. So it's really about capturing that behavior and being able to generate enough sufficient data about it to see whether this particular architecture is going to sustain, or is there going to be a bottleneck in the software behavior. When you model the storage system, one of the things you want to consider again is what level of detail you want to go into. Do you want to have it more stochastic, where I just randomly pick a random read or a sequential write or things like that, or do I actually want to put addressing, because I might want to look at very specific scenarios and understand why my hit miss ratio is below 40%. So for example, the models we looked at right over here, when I look at this one here, I simply have delays associated with access times, and I have a control, in this case an SRAM, so control is not really relevant. Or I can assemble up a lot more complicated, a lot more specific behavior. For example, in this particular design, where I've got many input interfaces that are connected through an AXI bus to a memory controller and hardware DRAM. Now notice here that the address is actually broken up into banks, rows and columns. So you can actually look at accessing a particular location in a particular bank. So in this case, we are almost matching, or actually are matching exactly what the hardware would do. So even the power consumption becomes very specific, because we look at different aspects of activate, refresh, read and writes, and be able to make power determinations as well. Now, network is a fairly broad area and is also quite complicated in the sense that, how do you get the sensor data to move from where it is to the compute platform or to the storage platform? What happens if I add more sensors or increase the number of devices that are shared on a network, or increase the number of messages that are being sent by different subsystems to others within the same topology? You want to look at how does the adding of the new nodes reduce the performance or increase the response time? What happens when I have more increased traffic, which is more number of tasks generated by the same set of applications? And also seeing what happens if I start migrating to multi-core and having custom connectivity between the cores itself, to look at ways how I can increase the amount of data I can pull out of this particular system. Now, analysis can be of many types. If I look solely at the processor, I might look at the pipeline activity, or I might look at the pipeline utilization. But what I might also try to see is, how much of thrashing is happening, which means, how many times the prefetching keeps on going to the memory. And these will create a large percentage of stalls. So other ways we can send it, maybe move from a burst to like a streaming based architecture to see whether the performance improves. Things that you can try and analyze. Now, in general, for most devices, you'll be looking at, what is the utilization, what's a buffer, component, looking at the end-to-end latency. Now, network latency, what you're looking at is, you have multiple gateways within a network, and then these gateways. So, for example, if I take this particular design, give me 1 second, I'm just selecting the right model to demonstrate. Oh, seems like I didn't select the model, but that's okay. We'll just pick, this system. So here, for example, you can see these are my connectivity between different devices. That's my distance, and that's my speed. Now, it's possible for me to shut down certain things, bring them back up, shut down certain compute storage, bring them back up, and see if my system can still meet the performance. Can it still handle the load if things like a connection or a compute actually is lost for a period of time? So here is an IoT system, an Internet of Things system, where we have a complete end-to-end architecture starting from devices that have a Bluetooth interface and some compute and a vast number of sensors, going through a hub that is connected to, all these sensors are connected to gateways, to different gateways, and then those are finally connected to the data center with a server in it. Now, what I want to do in this particular case, and let me move over to the tool again. Okay, here we go. So as you can see, we've got 5 different devices connected to 5 different hubs, and of course you can keep adding more and more devices to connect to a small number of existing hubs. Now here we're looking at redundant connections on the backbone. That's between these hub edges to the data center and back. And then we look at, for example, turning off the power. I'm sorry, turning off the link, and then seeing how the data traffic is moving across these alternate paths that are available or defined in the system. So in this particular thing, what I want to look at is, within each of these devices, what is my processing on the compute, and also looking at what is the power consumption on that particular system itself. For example, over here, you can see the latency of the data center traffic. But at the same time, what you can also look at is you can use, for example, see the amount of memory during the time period consumed by, say, in this case, the M0, the ARM Cortex M0. But you can also look at, how much the DMA was consuming, what was the IOs per second, what was the buffer occupancy. So you can get a variety of statistics that are all pre-described that you can then use to make the decision on whether this particular device can, if you put it on the network, what will be the impact on the network, or what will be the response time for this particular device. So for example, when I double click on this, you can see things like, what is the time between requests, the size of the request, but also, the processor memory speed and size as well. So it allows you to define very easily and very quickly the hardware aspect, and then run the simulation to look at what is the expected results we can get out of the system design. As you can see here, we're really looking at the MIPS that we can get out of the architecture and what was the latency for the task arriving at each one of the devices. So you can see, for example, here is one of the traces that we generate for the system. So you can see that we went through the RF node, through the router, to the edge, to another router, and then back to the device 4 RF node. So you can see how the data transfer, data movement is done across the particular network. So the model will actually trace all the flows and all the movements in the system itself. So that way what you can do is you can actually verify if all the flows are correct. Storage systems, again, I just talked about a little while ago, but the storage is all about how do I get easy access, that is, how do I get in and out of a particular device without having to spend considerable amount of power or considerable amount of timing. So we can do models where you can have the storage itself be central to the design and see what the performance is going to be for that, for a particular storage target. Like in this case, we have different types of flash and different types of disk drives, and you have a common bus for all of them, and then see, if I select one drive versus one flash versus another one, what's the performance degradation or performance improvement. The comparison can be on two levels. You can look at the power consumption between the two, or you can see the throughput between them, and you can see which one's better. In this case, just to set the stage, this is 10 to the minus 4 while this is 10 to the minus 3. So the disk drive is only about 1 millisecond, while this is about 0.1 millisecond for this particular workload and for this particular application. If I change it, the behavior might be entirely different. Now, one of the key things about system design is not just to do the analysis and do the experiments, but be able to communicate these analysis and experiments to the rest of the system. So one of the things we can do at Mirabilis Design is we can actually allow you to be able to share your descriptions or your models with others, either within the company or someone that's outside the company as well. So for example, when I look at this one over here, oops, sorry. So for example, I can look at, what's the setting for the values here. I can go inside of this block. I can look at what the power table is. I can look at, what's inside the server to understand more of its details. So I can look at what the parameters of the compute part of the data center is. So a variety of things that can happen here is this documentation can then be shared across the organization or even to partners or potentially to customers to show them If you upgrade to our particular device or you upgrade to the next generation, what is the performance improvement or what is the lowering of the power that you can get? Now, in summary, what I want to talk about is if you look at system simulation really allows you to take the guesswork out of your architecture exploration and to be able to thoroughly and completely test all the different architectural decisions, completely test all the different workloads and scenarios. The other aspect is that you can do a variety of trade-off analysis, simple things like, not simple, but main items like performance and power trade-off or partitioning across hardware and software, looking at doing a triple redundant versus a dual redundant, what is the uh, chance of failure, and finally be able to distribute an executable specification that goes across the entire organization. So allows me to provide completely an end-to-end mechanism to validate, to optimize, and also communicate my design. That is the practical application of system simulation within organizations today. With this, I would like to conclude my presentation today. You can ask any questions at this time, and I'll be happy to answer any of them.
Yes, I have a question in general. How is software modeling done in this case? How is the performance, what certain software task is consuming estimated?